But now we are looking at another model first to illustrate another point. So all these are independent of all this is independent of the linear state of the polarization. As long as we're driving it with the electric field that is oscillatory. So remember, we devise this model. We assume this we have an oscillatory electric field, but then it's independent of the polarization. What this vector is, we can the non-perpendicular vector. You still get exactly the same epsilons. So in other words, even circular polarization or the different polarization, you have the same epsilon. It doesn't depend on the polarization. Now the next one is a model that depends on polarization. Especially it depends on whether it's the circular polarization state, whether it's right-handed or left-handed. So that's there are medium that there are different kind of media that can have that property. In particular, is in plasma, or in this case, Jackson called it ionosphere, magnetosphere. Basically, in many plasma, you have this situation, and this is again a simplified model to illustrate that. Let's just start with about time, but then let's just start to describe the model. So you have assume you have a background electric field. So B, it's this is Jackson called B sub 0. The magnetic field is B sub 0, and it doesn't have the unit vector, but let's assume it's along the z direction. Okay. And then we are assuming that you have a wave that is also propagated along the z direction, so it's parallel propagation. So this is a simplification because the more general case is because you already define one direction, then propagation direction generally is not exactly in this along this direction. So that discussion is more complicated. So we'll just stay with the situation that n or the propagation direction is along z. The n is z, and obviously by our discussion before, for plane wave you can define the epsilon sub 1 and epsilon sub 2 as like a local Cartesian coordinate along the propagation direction. So these are two perpendicular linear polarization unit vector. But then we can also define the circular polarization unit vector that we defined before. Right, that is what we define. And now we consider the propagation of the electric field as the circular polarization. The E is the origin field intention. Actually, not with this square of 2. This was we have a magnitude epsilon 0. Well, just E, just E. And obviously, this is I. Along C, so it's KZ minus negative. Just assume you have a wave that is of this form. And obviously, we will try to divide the relationship between K and omega by a model, right? And the model is basically consider you have free electrons in this medium. This is basically a plasma. And consider the equation of motion of these electrons. So we can write down the electrons. So electrons is when you have electrons, then it's mostly it will gyrate around the magnetic field lines. right? And but then with the impulse wave, then the equation of motion electron will perform a circular motion. So write down the equation of motion. Double dot. So it's the acceleration times mass that should equals to the force. That, the force has two terms. The first is the Coulomb force law. Right? You have the EV cos B, but this is electron, right? So you have E, and then the V is X dot cos in the B is assume that B is just the total B sub zero. I mean, the wave has a magnetic field, but if you assume that the wave amplitude is very small, and especially the wave magnetic field is very small to compare with B sub zero, so the force is mainly just X dot cos in the B sub zero. Okay, so that is approximation due to the small wave amplitude, and so that is that, and then actually this is electron and Jackson use. I think that's a negative sign. There's a negative sign for electron. So negative E is the charge. E is assumed to be positive. And likewise, you have the electric field terms, the minus E electric field. This is a driving electric field because the wave is propagating the wave electric field will drive the motion of electron, and we ignore the wave magnetic field in driving the electrons because of the assumption that this is much smaller than B sub zero. Okay, and now we can try to solve it, except that we are about time. We'll do it later. It actually turns out to be quite straightforward with this epsilon. All we need to do is work out this term. I mean, one more thing, we ignore the imaginary part, the damping. Basically, we ignore the conductivity. There should be a conductivity term, or in microscopically, that should have a damping term or collision. There should be a collision frequency term. Right? But we ignore that for simplicity. We just try to look at a simple case that dispersion depends on the circular polarization. So ignore the collision. Okay, so we stop here and finish this discussion on Wednesday. All right, and we'll continue. And we are in section 7, the beginning of 7.6. We'll divide a simple epsilon as a function of omega, but is the dielectric constant or the speed or the refractive index depends on the polarization. Depends on whether it's left-handed and right-handed, and so we actually, I think we wrote down the first equation. This is a situation that we put the geometry. So you have a background magnetic field. It's B0. B0 and part of B0 magnitude in the Z direction. You assume there are free electron. Later on, we'll need the electron density capital N, and then you have electron, right? And you have electrons, they're negative charge, and Jackson use E as a positive constant, so charge is minus E, right? And the electron will rotate around with no electric field, will rotate around the background magnetic field. But then you are considering a wave, so you are imposing a E, which is Jackson term is with this epsilon 1 plus or minus epsilon 2, and then the magnitude E, and so it's single frequency, so you have minus omega t. And epsilon 1 and epsilon 2 are perpendicular unit vector relative to z, so you can say one is x, the other is y, so you have 1, so 2, that kind of thing. Okay, and remember the circular outlet is actually the circular polarization unit vector. You normalize it by 1 over square root of 2. But Jackson doesn't do that in here, but that doesn't matter. Okay, so that's the situation. You consider the one electron, the equation of motion. So it's electron m, electron mass m, and some displacement vector of it. Second time derivative is the acceleration. So that equals to the force. The force has the magnetic force. We are saying that is charge minus E, and the velocity is x dot cos B. And B, we are using just the B0, not including the wave magnetic field. And so, of course, the assumption is the wave magnetic field is much smaller than the uniform magnetic field. That's one thing. And another thing is that we assume that this is non-relativistic. For non-relativistic case, even though the wave has both electric field and magnetic field, but the force, Lorentz force, the magnetic Lorentz force depends on the velocity. The velocity much smaller than the speed of light. That magnetic force is much smaller than the force. So so that's we keep just the uniform field here, and then the electric force from this is minus E times E. Okay, so that's the equation 7.63. Except that to move this term to the other side doesn't matter. Okay, now the final solution, so you assume that assume x is also proportional to e to the minus 5. It's basically a driven system. We drive the electron with this wave electric field. Okay, so that if we move with the same frequency. All right, so that should be trivial because taking time derivative meaning multiplied by minus I omega, so this will pull out the minus omega squared. So omega squared, and we'll have and then multiply by x. But there's also an x here, so we'll put that to the same size. But then we'll actually do it a little later. Okay, we'll do it a little later because we need to work out the cost product first. Just keep it like that first, and then this will be just minus I omega, I e omega x cos into b calculating. Put the BCA over here, it doesn't matter, so minus e. And using this one here, epsilon 1 plus or minus L2 magnitude E, and let's just ignore all this either minus I. And the idea is that we have to figure out what this is just the timed property. I mean, the time dependency. So you need to figure out the x, what the x vector will be proportional. So that we'll actually use I think we can, because you have this unit vector here, in order to match the both sides, we can try and let's try x is proportional. This direction of x is equals to proportional to that, so it's equals to some magnitude x, and then so plus the minus. So do for either case, and then figure out the scalar. The scalar. Right. The reason of that is now we can consider how you do the correspondence with this vector. I mean, this is not normalized, but that may change. I mean, there's this magnitude will change a little bit. Right. I don't think that is important. I think we just have to normalize that. So let's consider x cos b, x cos c0. So this b sub 0 is just a constant. This is equals to x. So epsilon 1 cos into z, right? This is like x cos z is minus y. X cos z, right? X cos z is minus y. So this is minus epsilon 2. And x, this is epsilon 2 like y. X, but this is x cos z. The y cos z is x. Right, so plus or minus I. Okay. And the idea is that you can now pull out the plus or minus I as and divide epsilon 1 first. And the second term basically you are divided by minus 1I, which means you are multiplied by plus or minus. Right. You pull out plus or minus I, divided by plus or minus I. Right. And minus 1 divided plus or minus minus 1 divided by I is I. So it's plus or minus I. Epsilon 2. Right, did I get it correct? Can you follow it? So you basically pull out the plus or minus I over here. And the rest is divided by plus or minus. Minus 1 divided by I is I. And the plus or minus still plus or minus. Plus or minus I. Okay? And then so it's, yeah. Okay, so this term actually turns out to be also proportional. This term proportional, this one, except that you have plus or minus I. Yeah. You have I and then the plus or minus I. So let's substitute this one into here and group that together. Now we can group that together. So we have minus and omega square. And this one, after you substitute this into here, you get plus or minus I times I is minus 1. And you move to the other side, plus 1. Plus 1, but then you still have this plus or minus sign. So you can plus or minus I. Right? Plus or minus I. No, your I times I, your plus or minus the rest. E omega BC. Okay. That's right. And then this x equals to minus E times E. And you cancel all the unit vector. This one has a unit vector, this one has a unit vector. Yeah, this, I mean, not unit vector, this vector dependency. Cancel with this vector dependency. Only this is left. Now you can solve for x. X is you have a minus, cancel with the minus. And so it's E times capital E divided by m omega square minus plus E omega times okay, so that's x, and then obviously this x is going into here. That becomes the vector x, right? That will we need that would be 7.65. You put it back to here. That becomes a vector x, and then you combine this with E. That is that's electric field E. So that is 7.65. Okay, so you can write copy that x is E by Jackson pull out one omega. This becomes omega minus plus, and the rest is you pull out omega and m also. So you have E times B0 divided by omega. And that is defined here is omega sub B. Omega sub B is E, M. E is electron charge. This is electron mass. This quantity is for the electron cycle. You haven't taken parts now, right? So this is the electron cycle frequency. It's quite easy to derive that. It's just that like the electrons without any external force, then it just circle around. I mean, it can also move parallel to the magnetic field, which is irrelevant here. It always transform away the parallel electric field, a parallel velocity. Just consider circular motion. So you can say that it turns out that it will turn out according to the right hand rule. So we can figure out that by the force. Force is minus E and velocity. If it's moving along this direction, so the circle moving in this direction, and that's the velocity V, right? And then you have V cos B is actually vector. V cos B is outward. This is like a circle, outward of the circle, but you have minus E, so inward. So you move like that, the magnetic force will be pointing inwards, which is what is needed for the circular motion. Circular motion, you need the centripetal force. Okay, so, and the magnitude is E times B, EV cos B. So the magnitude EVB, that's the magnitude of centripetal force due to the magnetic force provided by the magnetic force, and that is balanced by the centripetal force, mv squared over r. Right? And then you can solve for V obviously. Just cancel that. And he's moving M over the other side. And the most important thing is that you calculate the time it takes to go around. The time it takes to go around is the circumference divided by V, so it's multiplied by 2 pi. And 2 pi. So 2 pi r is the circumference divided by V is the time it takes. That's the time. What is called the period. This is the cyclotron period. And one over period is the frequency. The 2 pi f is the circular frequency. So this is m omega. So omega is EB over m. That's what we call the cyclotron frequency, the actual cyclotron frequency, although we usually talk about using the term frequency for circular frequency cosmic physics. So, so we call that frequency, although this is actually is the circular frequency. All right, so that's the physics of this quantity. All right. Okay, times E. Right. Now we're about to get epsilon by just counting how many dipoles. So each dipole has a dipole moment minus E times X, right? And then you multiply by the density. That is how this becomes dipole density. Dipole density is what we call the polarization. I mean, not the same as the wave polarization. It's the same terminology, but it's the polarization of the medium. That's basically a dipole density, electron density, and each dipole has minus E times X, right? And so we substitute this into here, so it's minus E is minus N, and then you have extra E, the E squared, and then E and divided by M omega minus plus omega sub D. Okay, then you derive the epsilon. So D is given by epsilon 0 E plus P. This is what we learned in chapter 4, right? And then you substitute this into here and group all the E together. So that is epsilon 0 minus E squared M. We actually want to pull out the epsilon 1. Yep, M. Epsilon 0 M. Then omega minus plus omega sub B. Okay. And M times E. All right. Then by the definition, this whole thing is your epsilon, right? D is epsilon times E. And epsilon is depends on frequency. And also the polarization, circular polarization, you have minus plus sign. So epsilon omega is epsilon 0 and 1. And we already defined this density times E squared divided by epsilon 0 M is what we call the plasma frequency. And this is called the electron plasma frequency because we are using electron density and electron mass. Minus omega P squared, or some people would like the omega PE squared, the electron plasma frequency. The square of that. Did I get? Yeah, this is electron. This is not ion. This is Z term. Last time we have this for the molecule. So that's the number of charge in each molecule. Okay, so that's different. This is just electron. This is electron density. Okay, and E squared of epsilon 0 M is that, and divided by omega minus plus omega sub B. Okay, so that would be the dielectric constant. I mean, some people, most people divide by dielectric constant divided by epsilon. So divided by epsilon, we call it dielectric. But I usually don't care about it. They call it Hounsing dielectric constant. Because in Gaussian, you don't have that separation. Gaussian epsilon is just epsilon divided epsilon sub 0. Doesn't matter. You don't have epsilon sub 0 in Gaussian. Anyway. Okay, so that is the model. And let's say for 7.67. So the major thing is that from this this epsilon can depend on the circular state. Where there's the minus sign here is what we call the right-hand rule according to the plasma physics or the atomic or whatever high energy physics. Then according to optics would be left-handed. But it means this minus sign this right-hand rule is to propagate. If you have a wave that propagate along Z, the right-hand one will be the electric field will circle. There will be an electric field. The electric field will circle around the the one fixed space, fixed location. The electric field rotate in time according to the direction of the finger. So that means you rotate this and that, you rotate in time that way. The right-hand rule. And by the discussion we had for this electron cyclotron motion is in the same sense as the electron. The electron moving with this the same right-hand motion. As if your electric field for the right-hand wave, the minus sign, the electric field will move at the same sense, rotate it in the same sense as the electron rotate, right? And if the wave frequency omega is matching the gyro frequency of the electron, so then it means that you think about an electron that gyrating, you always see the same electric field. The electric field is following it as it rotates. The electric field is putting a force on the electron, but as the electron rotates, the electric field following to rotate. So you keep rotating it, supposedly you electron will gain energy this way. And so therefore the whole thing will blow up. Of course it won't blow up, but this blow up, this singularity is represented by this minus sign because if omega equals omega sub b, you have a zero in the denominator. So the dielectric constant actually blow up at that point. This is called the electron cyclotron resonance. Okay, and that is due to the sense that the circular polarization is moving and rotate in the same frequency as the electron cyclotron frequency. That you get this resonance situation. And you don't have this part for sign for electron doesn't have that. But if you have a plasma with positron, then the part sign becomes resonant. Okay. And obviously, you have you consider cyclotron motion not just electron, and you add ions, free ion, this charge, but this charge positively, then you will have an extra term that with the omega, when omega equals to the ion cyclotron frequency, then the plus sign will resonate because ion will move in the left-hand sense because the charge. If you change the charge, change the sign of the charge, it will rotate the other way. Okay, so ion rotate the left-hand sense. So the left-hand wave will have a resonance if the omega is the same as the gyro frequency. In that case, ion gyro frequency, that will have the resonant ion cyclotrons. Okay, so those coming from the consideration of this epsilon, right?